Well, good morning again, everybody. All right, so now we're going to talk about the edge-triggered flip-flop. Looks kind of complicated, but we're going to have a few little breakdown areas of this that'll hopefully make this a bit simpler. If you notice, there's kind of a structure to this. So there's really kind of, if you look in here, I've got a series of SR latches. I've got an SR latch with one extra input. This is a straight SR latch where I'm just reading the output values twice. Right? So that's internal. So you can imagine that's the line of the SR latch being grabbed. So that's my second SR latch. Um, this one is also an SR latch with one extra input. So you can kind of imagine um, I've got, for this case, two of the S primes. So I put the primes here because these are the NAND style. So we have to remember we have to do the whole prime thing. Um, And I have one final one, and this is just a standard SR latch that's going out. All right. It is clocked, so that gives us our ability to handle and enable. So we're going to walk through two different cases. What happens when it's a clock 0 and it goes to a 1 and D is equal to 0, and what happens when D is equal to 1. Now, why do we start with clock equals 0? Well, consider clock equals 0 here just for a case. Oops, Ben, come on. Okay, if clock is equal to 0, now 0 goes to a NAND gate. So just remember the AND again for a second. 0 goes into the first part, the AND, and we'll deal with the inverter in a sec. 0 into an AND, I don't care what the other value is. 0 and something is just 0. Inverted, it's a 1. So it's guaranteed to be a 1. The same thing happens to this NAND gate. I don't care what the other values are. It's going to be guaranteed to be a 1 because of that. Now, this is what's so important. So I don't have to worry about the D values yet because D is irrelevant. Both of these are driven to be 1 when clock is equal to 0. And if you remember, two ones on the input into a NAND style SR latch is going to guarantee that it's going to hold. So clock equals 0. Maybe that's worth making a little note too. Let me see if I can find there's my text tool. That's almost a useful spot too. So we can say clock equals 0 is hold. So therefore I only have to worry about what happens when it goes to a 1. And we'll talk about and show you that during 1, it's we'll just read right at the very beginning and then nothing else will matter, which means we only need to worry about that transition. So that's going to be basically the nature of how we show things. And since we won't care after that initial sampling, D can change all at once. It won't matter at the transition from 1 to 0 because we don't care. It's no longer looking at it. So this is a very important little observation. All right, we'll return to our text tool here. So we're at clock 0. Now let's do the first case. D is equal to 0. So I'll put my D is equal to 0 here. So again, since D is equal to 0, this NAND gate is going to output a 1. So now I've got a 1 here. So this one, stop that. Okay, there we go. This one's going to go all the way around this wire, come back, and that comes in here. So now I've got a 1 coming in, and a 1 from here comes up. So I've got two 1s coming into this. 1 and 1 gives me a 1, and then the negation bubble will give me a 0. And my pen, that gives me a 0. So I don't know what these are, but it's what it used to be. Okay, so that's my underhold, and now we know what all the intermediate values are. Now let's let clock transition to 1, but this is a sequence. So this has just happened. This is all set up. And now, sorry, wrong one. The clock turns to a 1. So when clock turns to a 1, this is no longer holding these values, but they still might be okay. Because watch, for instance, here, I've got a 0 on this. So this 0 on here is going to force that to stay a 1. This is kind of already in a stable position. So unless somebody tells it to do something different, it's going to be pretty happy staying there. On this one, I've got a 1, I've got a 1, and I got a 1. So they're all 1s. And 1s into the first part, the and, gives me a 1. Inverted gives me a 0. So this is going to want to change to a 0. Now, at the initial instant, this is still 0. So that's going to force this to be 1. So it didn't matter what that line was. So for that initial instant, that's going to be there. And then I will have a 1 coming around here, the same value it had. And I've got a 1, 1, NAND 1. We've talked about this a whole bunch. Gives me a 0. So right now, all of these are now stable. Well, the only thing that changed was this value right here when that changes to a 1. At that point, I've got 1, 0 coming in. So you can either look back on your notes on here, or we could just quickly kind of analyze this again. Um, these are the kind of prime symbols. You could also just kind of remember it's the opposite, right? When it's 1s, it's hold. Whichever one goes to 0, that's the one being asserted. Um, or you could actually, if you really want, you could kind of do the analysis. 0 goes into a NAND gate, which is going to force a 1, which means I'm going to have 2 1s on this NAND gate, which gives me a 0. I don't care which way you do it. So the second it goes to clock 1, that's going to force, as long as D is equal to 0, thank you, no, that's going to force such that, I'm going to get the text tool. It's not quite like drawing. Come on, yeah. Oops. I forgot it creates a text blob. Okay. So that creates Q. Hello, Q equals 0. Yay. So when it does this, right, so this is the data value, right? Whatever value goes here has ended up here. Now what happens? Clock stays 1, and let's let D now, right? Next thing down the line, let's get another text box up. Maybe I should have been so hasty at doing that. Let's let D transition to 1 now. Oops. D transitions to 1. What happens now? So we've gone through this. We've seen this. Some point later, before the clock changes again, D changes to 1. Does it affect anything? Obviously, if D changes to 0, it's not going to do anything. So what matters is what happens if D goes to a 1. Well, if D goes to a 1, it's coming into this, but I have a 0 here. So this 0, this is the only spot D goes. This 0 comes in, and I've got 0 and 1, which is still 0, negated, it's still 1. So that 0 right there, effectively, the second it gets created, which happens right at the beginning, remember that's the only bit that flipped. The second that one gets flipped, at the start of this transition time here, The second that happens, it's all over with. That zero basically turns off the ability to read the value on D. I'm, nothing can change. It's just ignored. So when D is initially zero, right at that transition zone, it causes, by coming through here, right, it's initially one, right, this one here comes around and everything else is one coming in, boom, it just turns that to a zero and it locks that gate down hard. And this doesn't read anything ever after. So after that point, D equals 1, well, who cares? We get just, great, your D turned to 1. It still means that Q is equal to 0. All right, I'm going to move my little clock timer. I don't know why it drops it over there. Okay, so let's consider case 2. So we're going back in time now. We've got on this, our clock is going to be equal to 0. And we're going to we'll clear everything out. Okay. So if you remember, when a clock is 0, it's going to, because of these 0 into these NAND gates, give me 1s on the output, which puts it into hold. Now we've got D is equal to 1. That's our case 2. We're assuming D is equal to 1 now. So that means I've got 1 and a 1. That forces this to be a 0. The second that's equal to a 0, right, because these are both 1s, this comes around and this is a 0. So 0 NAND anything is going to give me 1. And then these, it doesn't matter what it is. So now I've kind of got everything set up here. So this is kind of a little different than our last setup. If you remember last time, we had that one down here. So, these two ones are always the same, but you'll get different values here. This one was already stable with the 0, 1. This is already in a stable position, holding a 1 on this. So this is holding the reset pretty hard. Okay, now we're going to now change, and clock goes to 1 now. Okay, so let's take a look at them each in turn. Right now, the top one, at the initial instant, we still have a 1 coming from here. I still have a 0 coming from here. So that still is going to want to initially keep that a 1. For this one, I've got a 1. I've got a 1 now. So that's going to want to make this equal to a 0. Now, that's going to happen. That'll be its first transition. But right at the very start, this will still be a 1. It still takes it's a little bit of time, right? So there's still kind of a 1 here for a little bit of a moment, right? But it doesn't matter because I've got a 0 here, and that 0 is going to make it ignore it. So that little transient 1 at the beginning is irrelevant because I've got the 0 here, and that 0 is going to keep this 1. So basically that 0 made it ignore everything else anyway. And then I've got these two 1s that are going to force it to be equal to a 0 here. All right, so that forces us now to go to this 0, 1 into this, which means a 0, 1 asserts S prime, but does not assert R prime. So I'm doing a set, which means Q gets a 1 and Q prime gets 0. So this condition, when I switch from here, goes from hold, and I'm getting better at that. Okay. And we end up with Q is equal to 1. So again, right at that instant of transition, whatever the value of D is, whatever is the stable value, and realize it's got to be there before and after. It's right across that transition zone. At that instant, whatever value gets in, that changes the output. Now, what if after that, at some point, we end up, let's get a couple bits of text here. What happens if D changes its value? Obviously, if it's equal to 1, we already see that that's consistent. What if we take a look at D switching to a 0? And what will that mean? Okay, that was interesting. It evidently does try to interpret what I'm drawing. Guess that's both good and bad. Okay, so we now want to see what happens when this value changes. It's in sequence, so all those values are still there. Okay, so D is now 0. A 0 goes into a NAND gate, and we know that that is going to force this to become a 1. It does not matter what else is going on anywhere else. That is an overriding situation. So that means essentially this is not going to go, but this is already a 0. So that 0 coming in ignores these two inputs. It ignores what the value is here. That 0 is going to force this to stay a 1. So as long as that one doesn't change, this one won't change. And D, as long as it stays 0, this stays a 1. And if it goes to a 1, this will go back to a 0, but this will be flipping as long as it doesn't change this. This is the only one. We've already shown this one doesn't matter because that one's locking it out. Right? And that's the reason this crossover wire is so important. As long as this one flipping with D doesn't change this one, then there's no way to alter this. So that's the only thing we have to check now. Now, initially we had that 0 that came in, which is a 1, but notice this is a 0 here. So this 0, 0 NAND anything, still forces a 1. So this one flipping, coming in, it's ignored because this 0 locks it out. So since this 0 is kind of guarding the gate and preventing it, it doesn't matter how this one flips. This one can flip all day long. It's not going to change this value. And if it can't change this value, it can't change that 0. So as D flips, it'll flip this, but it won't change any of these values, which means it doesn't change these two values, which means it doesn't change the input to this SR flip-flop, which means it doesn't change the outputs, which means Q is still equal to 1. And the value of D is irrelevant at that point. So it only reads it at the clock. Again, it only reads from a 0 to 1 transition. That's the whole thing. When clock goes 0 to 1, it'll read D. All other time periods, totally irrelevant. Does not matter. So that's kind of our big thing on this. So I notice this one has now run kind of 20 minutes. This is a more complicated circuit. The big takeaway from here, though, is you can now see a second way we can build an edge triggered flip flop. And these are kind of our crucial styles here because these flip flops, this is what we want to use from now on. Because the edge triggered flip flops, right, pos edge or neg edge, allows us to remove a lot of errors. And this gives us now a reliable memory unit upon which to build all the rest of our designs. So the rest of the course is just going to use these. It'll become a box. It's going to have D and it'll be a clock and we'll have Q. We usually only show Q. We could do Q prime. You can see it's trivial. All it has to do is run the Q prime wire out. So it's there. It's easy to grab, but we usually only need the Q because we're typically dealing with the straight signal. Um, but at any point, I could just decide, hey, I want Q prime, and I act like it's free because it is free. It is right there implicitly. We usually just don't want to mess up the drawing. So all right, well, we have kind of made it through this part of the explanation, and hopefully this is a little bit better than the initial pen casts. I still am doing these drawings with the pens. I hope these are good. I've tried drawing by hand these things, or sorry, inside the computer, and the initial drawings, I'm not going to claim to be a computer artist. I'm more a paper and pen type guy, or whiteboard. So hopefully this helps, and we'll do a few of these, and we'll also try to keep doing the online meetings, probably about online meetings once a week, I think, just so we can kind of answer questions and go on. So if these work, then that will hopefully give you a good, robust variety of ways to stay up on the material. So I hope you're all doing well, and I will see you at our next online meeting. God bless.